right, so we are back to kinematics with displacement, velocity, and acceleration. And we learned in our derivatives unit that you could go take the derivative of displacement and get your velocity formula. Take your derivative of velocity and get your acceleration formula. So now that we have integration, well, now we can either work in one direction or in the other direction. So we can find, if we have our velocity formula, we can integrate and get back and find our displacement formula. So now you just really have to think, which way am I going? Because if you go the wrong way and when you're trying to figure something out, you'll get a totally different equation. So here's whoops. All right. So we got an acceleration formula. So I don't know if it's going to be helpful to write sva off to the side so you can remember which direction you're going or not. But we've got a formula for acceleration. Acceleration is t plus 1. We want to find the equation for velocity and the equation for displacement. And we're given some important information. That when t is equal to 0, the velocity is 8 and the displacement is 0. So starting off, we have acceleration, and we're going to want to work backwards to find these other ones. So integrating once will give us our velocity formula. And this is an easy integral to do. But we get plus c. Any ideas how we can figure out that c? Well, we're given that at t equals 0, the initial velocity is 8. So sometimes this appears in a question where they actually say when t equals 0, v equals 8. Sometimes they'll hide it by saying the initial velocity, and anything that's initial happens when t equals 0. So in this case, when t is equal to 0, the velocity is 8. Well, that's very nice when they give us an initial velocity because it's easy to plug in. And we get that c is equal to 8. So now we can write out that our velocity formula is t squared over 2 plus t plus 8. So now to find our displacement, we're going to integrate again. With respects to t. Does that look like a t? Maybe not. Nice. So again, integrating, add 1 to the exponent, divide by 3 will give us t cubed over 6, t squared over 2, that's 8t. I'm going to use the letter d this time because I used the letter c. The last time when we figured out c was 8, so when you're working within the same question, you don't want to reintroduce a variable twice because we already figured out c was equal to 8, and it may not be that this value is going to be the same. Again, we're told that the initial displacement was 0, so when t is 0, s is 0, and most likely this would be on the calculator section, so you could type that in. Luckily, I did it beforehand. We get t is equal to 0. So now we can write out that our final displacement formula, t cubed over 6 plus t squared over 2 plus 8t, is our displacement. So again, we find that these kinematic questions generally aren't that difficult. The numbers that they use aren't that difficult, and it's just a matter of knowing the overall idea of which way you're working, either to integrate to work backwards or to take the derivative to work forwards. So this is second example, starting in the middle. They've given us a velocity formula. So if we want to find the acceleration, we'd have to take the derivative. So the derivative of that function is just going to be negative 10. And there's our units. No problem. If the initial displacement is 40 meters, find an expression for S. So here S is working backwards. So we set it up, and we just need to integrate. And when t is equal to 0, the initial displacement is 40. So now we can write our equation. All right, this third one I'm going to get you guys to try. All right, let's do a check how you guys did on the first ones. So since we have acceleration, we're going to integrate, and we know our initial velocity, so we can find out that our c value has to be 3. Then in part B, integrate again. Again, I'm introducing a different variable now because we already used c in the first one. You can solve that k is equal to 2. Now in part C, when something says a particle is at rest, you have to decide, what do I know? I know if it's at rest, do I know something about the acceleration? Do I know something about the velocity? Do I know something about the displacement? Now when something's at rest, it's not moving. For example, if you throw a ball up in the air, there's going to be an instantaneous moment where it stops going up and starts going down again. And at that instantaneous moment, it's going to be at rest. What do we know about it at that point? Well, the acceleration due to gravity is still negative 9.8. But we do know that the velocity at that point, since it's changing from having a positive velocity being thrown upwards to a negative velocity going down, that our velocity is going to equal to 0. So we're going to have to use our velocity equation, put it equal to 0, and then solve. Now there's kind of a hint that you're not going to use the displacement formula in part D, because if you'd use the displacement formula and then it asks you to find the displacement at those times, well then it would be kind of a redundant question. So once we found out 3 seconds and 1 second, we can just plug those into our displacement formula. Again, it's just a bunch of fractions and mental math, so it's not too bad, but maybe a little bit time consuming. So there's a difference between displacement and distance. So for example, you throw a ball up in the air for 2 meters and then you catch it again at the same place. The displacement would be 0, but the distance traveled would be 4 meters. That's why I probably don't enjoy running, because get out of my house, and if I'm going to run around the block for some exercise, like half an hour later, I'm exactly the same place that I started from, and I could have got there a lot quicker had I not gone for the run. So That doesn't help me with my exercise routine, so I have to find other things like play soccer. At least I have to kick a ball. I'm not sure. Anyways. So displacement is easier to figure out because you can just use your formula because it doesn't have to take in the fact that sometimes there's negative values. But if you want to find your distance, then you have to find out, well, when am I traveling forward and when am I traveling backward? And wherever I'm traveling backward, that would give me a negative area under that curve. So then we have to introduce some absolute values. So if you have your velocity formula and you're wanting to find distance, you not only have to figure out, well, what's our displacement formula, but you also have to figure out where is that part negative and where is it positive so that we can calculate each of those things separately. So here's an example where we're given a velocity, 1 minus 2 sine 2t. And we want to find the displacement over the first 3 pi over 4 seconds. Right? Because that's very typical when you're thinking, I wonder how far that goes in 3 pi over 4 seconds. So first of all, if we integrate this function, we're going to get a formula for our displacement. And the integral of sine is cos. And because it's a chain rule with a 2t in there, you'd have to divide by 2. But having that 2 out in front to begin with will cancel out. And also because the derivative of cos is negative sine, since you're integrating a sine, you're going to have a negative cos. So that's why the sign changes from a negative to a positive. So we can just plug 0 to 3 pi over 4 in there for the displacement. Plug everything in. You can leave your answer as 3 pi over 4 minus 1, or if you want to plug it into your calculator, you're going to get 1.36 meters. So this could be a non-calculator question because all of those values are values you know. So now if we want to find the distance traveled over the first 3 pi over 4 seconds, we're going to have to look at what's happening here. So in our velocity function, when it's graphed, we notice that some of it is below and some of it is above. And if we took our original function, so we could find these intercepts by graphing 1 minus 2 sine 2t. We could also find it by solving it. So here's our solving question, how you go about solving. It's a multi-revolution question that we used to do, where you have a 2t inside of the function. Well, just solve it like you would normally. 1/2, that's a value that you know. It's part of the pi over 6 family. It's positive. So you'd think in quadrant 1 and quadrant 2, pi over 6 and 5 pi over 6. Now that's what 2t would equal. So then solving for t, you could just divide both sides by 2, and you'd get your first 2 answers. If we wanted to go further, you could find other places that it's going to intersect again. But since we're only figuring it out in the first 3 pi over 4 seconds, this is going to be enough. So as far as setting up our integrals go, it's going to be positive between 0 and pi over 12. It's going to be negative between pi over 12 and 5 pi over 12. That's the red section here. And then in the purple section, it's positive again. Now, because of the pi over 12s, you could have solved the pi over 12s like we did on the side there without our calculator. But once you're having to plug those things in, now all of a sudden, well, gets a little bit more complicated. And so if you went to your calculator, these are the answers that you would get. So again, we have to make the decision. If this is a calculator question, this is a lot faster to do with our calculator than it would be to plug all those values in and subtract and integrate. If it's a non-calculator question, well, then you have to go through the process of plugging it in. But we have to be aware of what technology we have available, how we can use that, and what is going to get us to the point that's going to be the fastest. Because your exam is going to be 90 marks in 90 minutes. And some of the marks, usually the first 40 marks, you'll want to try to get that done in 20, 25 minutes. Because the last 40 marks, the last 40, 50 marks are going to take longer. So you know that there's going to be some of those questions that are going to cause you to think in there. So you want to be able to do things as fast as you can when you can do them.